In section 5.2, you will learn about natural log and integration. First up, we will take a look at integrals leading to natural log. Since the derivative with respect to x of the natural log of the absolute value of u is equal to u prime over u, it follows that the corresponding integration would be the integral of du over u, which is the same thing as saying the integral of 1 over u du, would equal natural log of the absolute value of u plus c. Remember that integration and differentiation are inverse operations. The derivative of natural log of absolute value of u is u prime over u, which is du over u. So then that means the integral of du over u has to be the natural log absolute value of u plus a constant. Now, in its simplest form, we could have an integral that looks like dx over x, which is the same as the integral of 1 over x dx, and that would equal natural log of absolute value of x plus c. Now, what to look for when setting up the integral? You want to get the numerator to be the derivative of the denominator so that your integrand becomes du over u. So let's take a look at an example. In this example, we have to integrate 1 over the quantity 3x plus 2 dx. So let's explore our strategy where we want to get the numerator to be the derivative of the denominator. So since we want u in the denominator, let's let u equal 3x plus 2. Then du is going to equal 3 dx. So that means we can set up our x integral here. We have 3x plus 2 in the denominator, which is where we want it. We have this dx that's in the numerator, and it's multiplying a 1. What we wish is that it was multiplying a 3. So if we put a 3 here, we can counteract it with a 1/3 out front, and now this integral is exactly the same as this integral. We just have this multiplying by 1 in the form of 1/3 times 3. Now we can substitute and write this integral in terms of the u variable. So let's bring down our equal sign. We have this 1/3 out front, so that will stay the same in the new integral because it's a constant, 1/3 integral. Now this numerator, 3 times dx, we see can be replaced with du, and then in the denominator we have a 3x plus 2, which can be replaced with the u variable. Now this is equal to 1/3. We have the integral of du over u, which we just learned that integral is equal to the natural log of the absolute value of u plus a constant. And because this is an indefinite integral, we have to go back to the x variable. So this will be equal to 1/3 times the natural log of the absolute value of 3x plus 2 plus a constant. this example, we have to integrate the quantity x squared minus 1 over the quantity 4x cubed minus 12x dx. We see that the degree of the denominator is 3 and the degree of the numerator is 2, so it certainly looks like we could have the numerator be the derivative of the denominator. So let's work on that and let u equal 4x cubed minus 12x. Then du is going to equal 12x squared minus 12, put that in parentheses, dx. We see that we can factor a 12 out, and we would have left inside x squared minus 1 dx. So all of that looks very promising when we compare that to the original integral. So now let's set this up. We have our x squared minus 1 and the dx that are in the numerator. In the denominator, we have 4x cubed minus 12x. So this is exactly the original integral. Now what we want to do is multiply by 1 in the form of 12 times 1 over 12. The reason we do that is so that now we will be able to do our substitution to the u variable. And this is going to equal, this constant out front remains out front as a 1/12. Then we have the integral, get our fraction bar in there, and this whole entire numerator is going to get replaced with du. And in the denominator, that 4x cubed minus 12x can be replaced with u. Simplifying, we have 1 over 12. We know that the integral of du over u will be the natural log of the absolute value of u plus c. And because this is an indefinite integral, we have to go back to the x variable. So this equals 1/12 times the natural log of the absolute value of 4x cubed minus 12x plus c. In this example, we have to find the area under the curve f of x equals 1 over the quantity x natural log of x on the interval 2 to 4. We know that area is equal to the definite integral from 2 to 4 of our function 1 over x natural log of x dx. Now we know that we always want to look for one part of the integral to be the derivative of the other part. And if we let u equal the natural log of x, then du is going to equal 1 over x dx. And we see that we have that in our integral. The 1 over x here, and then we could move it over by the dx. So let's just reorganize our x integral a little bit. Integral from 2 to 4, we would have 1 over the natural log of x times 1 over x dx. Now we are ready to substitute to the u variable. Now, in order to do that, we see that we will need to change our limits of integration over to the u variable. So if x is 2, then u is just going to be the natural log of 2. And if x is 4, then u is going to be the natural log of 4. So then this integral in the x variable, when it gets changed over to the u variable, these limits of integration have to change as well. And instead of integrating from 2 to 4, we are going to integrate from the natural log of 2 to the natural log of 4. This 1 over natural log of x, since the u equals natural log of x, then 1 over natural log of x can be replaced with 1 over u. And then finally 1 over x dx, that can get replaced with du. So now everything from our original integral in the x variable has been switched over to an integral in the u variable. Now, applying the fundamental theorem of calculus, we get that this is equal to the natural log of the absolute value of u, and instead of putting a plus c this time, we have to evaluate from the natural log of 2 to the natural log of 4. So then this will equal natural log of the absolute value of natural log of 4 minus natural log of the absolute value of natural log of 2. And this would be the exact form of the answer. And then suppose we wanted the approximate answer. Let's go to maybe the thousandths place. So grab your calculators. Try plugging in this expression. Once you evaluate the natural log of 4, you will discover that that is a positive number, so you don't have to worry about those absolute values right there. Same for the natural log of 2. It's going to be a positive number. Now, you know both of those are positive because if you made a quick sketch of natural log, you know that it crosses the x-axis at 1. So then the natural log of 4 is over here somewhere, which is a positive number. And the natural log of 2 is over here somewhere, which is also a positive number. Now, if we plug those into our calculators, we would get approximately equal to 0.693. In this example, we have to integrate 1 over the quantity x natural log of x to the 8th dx. Here we can rewrite this using the properties of logs as the integral of 1 over x times 8 natural log of the absolute value of x dx. Remember that when the exponent is even and it's possible that x could be negative, we have to put the argument x in absolute value symbols. Because this 8 is a constant, we can bring it out front. So we would have 1/8 times the integral of 1 over x natural log absolute value of x dx. If we let u equal natural log of the absolute value of x, then du would equal 1 over x dx. So we can reorganize our integral a little bit, and it's equal to 1 over 8 times the integral of 1 over natural log absolute value of x times 1 over x dx. Now we're ready to do the substitution into the u variable. We have this constant of 1/8 out in front, and that's going to come right down and stay a constant of 1/8. Integral. Here we have 1 over the natural log of the absolute value of x, and because u is defined to be the natural log absolute value of x, this becomes 1 over u. And then 1 over x dx, we see that we can replace that with du. Then this becomes 1/8. We know that the integral of 1 over u du is the natural log of the absolute value of u plus c. And because this is an indefinite integral, we need to go back to the x variable. So this is equal to 1/8 times the natural log of the absolute value of the natural log of the absolute value of x plus c. So it's necessary for us to have these two different sets of absolute values. Remember that the range of the natural log of absolute value of x is going to be all real numbers, which includes negatives. So that's why we have to have two sets of absolute value symbols here. Now, having this technique of integration which results in the natural log function allows us to do integrals of trig functions. Here we want to integrate tangent x dx. So if we first rewrite tangent of x as sine of x over cosine of x, and then of course we have the dx still, and now we let u equal cosine of x, that denominator, then du is equal to negative sine of x dx. Because we have sine of x dx, the only thing missing in our du is this negative sign. So if we multiply by -1 on the inside and multiply by -1 on the outside, all we've really done is multiply by 1. So now we can rewrite our integral. We've got that negative out front, and that has to come in the new integral. Then we have the integral symbol. Let's make our fraction bar. In the denominator, we have cosine of x, and that is the u variable. In the numerator, we have negative sine of x dx, And we can see from our definitions over here that that is du. So now that we have the integral of du over u, we know that this is going to result in the opposite of the natural log absolute value of u plus c. And now because this is an indefinite integral, we have to go back to the x variable. So this is negative natural log absolute value of cosine of x plus c. So now for the first time, we are able to integrate tangent of x dx. And see that it is negative natural log absolute value cosine x plus c. Next, we want to integrate cotangent of x dx. So let's first rewrite that as the integral of cosine of x divided by sine of x dx. Then we can let u equal the denominator, sine of x, and du would equal cosine of x dx. So now here, we don't even have to make any changes to this integral. We can go right to our substitution. So in the denominator, we have sine of x, which is going to be replaced by u. And in the numerator, we have cosine of x dx, and that's going to be replaced with du. We know the rule for integrating du over u is that it becomes the natural log of the absolute value of u plus c. Because this is an indefinite integral, we have to go back to the x variable. So this is going to equal the natural log of the absolute value of sine of x plus c. So now we know that the integral of cotangent of x dx is equal to natural log absolute value of sine of x plus c. Next up, we learn how to integrate secant of x dx. Now, to accomplish this integral, we have to be a little more creative. So if we integrate secant of x dx, we are going to multiply by the following rational expression. This is still just multiplying by 1, but it's in the form of secant of x plus tangent of x over itself. Now what happens is we get the integral. Let's make our fraction bar. And in the numerator, this secant x is going to distribute to both of these terms inside the parentheses. And we get secant squared of x plus secant x tangent of x. And in the denominator, we have secant of x plus tangent of x. And then we still have this dx we need to bring over. Now, let's let u equal this denominator, secant of x plus tangent of x. Then du is going to equal, we know the derivative of secant x is secant x tangent x. Bring down the plus sign. And the derivative of tangent of x is secant squared of x. Put that whole expression inside a set of parentheses, dx. Now you can see why we did that, because du, this entire expression here, is already there in our integral. So we can do this substitution. So let's bring down our equal sign and make the integral symbol in the fraction bar. This denominator right here, we have defined to be our u variable. And in the numerator here, secant squared of x plus secant x tangent x times dx, that whole entire thing we can see appears right here, and that gets to be replaced with a simple du. Very powerful substitution here. We know that the integral of du over u is equal to the natural log of the absolute value of u plus c. So now we know that the integral of secant x dx is equal to the natural log of the absolute value of secant x plus tangent x plus c. Next up, we want to integrate cosecant of x dx. Now, using the previous example as a guide, where we integrated secant of x dx, I want you to pause the video and try doing this one on your own. Then restart when you're ready to check your answer. So once again, we will want to multiply cosecant of x dx by a clever form of 1. And this time, the form of 1 we will use is cosecant of x plus cotangent of x over itself. Now this is going to equal the integral. Get that fraction bar in there. Once again, we can multiply the numerators together. So we are going to get cosecant squared of x plus cosecant x cotangent x. And in the denominator, we have cosecant x plus cotangent x. And then don't forget about that dx that we have in there. Now, if we let u equal the denominator, cosecant of x plus cotangent of x, then du is going to equal negative cosecant x cotangent x, and then it would be plus a negative cosecant squared. So we will subtract cosecant squared of x, put that whole thing inside a set of parentheses, times dx. Now we notice that we can factor out a negative sign, so let's pull that out front. And then we have cosecant x cotangent x plus cosecant squared of x close the set of parentheses, times dx. So now, pretty easy to see, we almost have du. The only thing we are missing from du is this negative sign here. So we can put a set of parentheses around this numerator, multiply by -1 on the inside, and counteract that by multiplying by -1 on the outside. All this means is we multiplied by 1. Now we are ready to do the substitution. This becomes negative integral. We've got the fraction bar. In the denominator, we see that over here in our definitions, that's just equal to u. And in the numerator, this whole entire thing we define to be du. Now this is going to equal the opposite of the natural log of the absolute value of u plus c. Since it's an indefinite integral, we have to go back to the x variable. So now we see that the integral of cosecant of x dx is going to equal negative natural log absolute value of cosecant x plus cotangent x plus c. So here I've made a summary box for you of the trig function integrals, where each trig function is isolated. The integrals of sine of x and cosine of x we already knew. But now that we have a technique for integration resulting in natural logs, we were able to do the integrals of the other 4 isolated trig functions, meaning tangent of x by itself, cotangent of x, secant of x, and cosecant of x. Now you'll have to work hard to remember all of these and memorize the formulas, but there's a couple of tips I can give you that help me remember. I know that these are natural log functions, and so the integral had to be set up as a du over u. And for tangent, I know the denominator is cosine, so that's who's going to be inside the log function. And for cotangent, I know the denominator is sine, so that's who's inside the log function. I also know that the derivative of cosine is negative sine, and that helps me remember that I put a negative. So since the derivative of cosine is negative, there's going to be a negative out here. Now for the integrals of secant x and tangent x, I kind of use their derivatives to help me. Because I know the derivative of secant x is secant x times tangent x, that helps me remember that the integral is going to involve the natural log of secant x plus tangent of x. And I use the same memory technique for cosecant, because the derivative of cosecant is negative cosecant x cotangent x. Then I know the integral of cosecant x is going to involve cosecant x plus cotangent of x and be negative. So if those help you, please feel free to use them. Always a good technique is to write these down 3-4 times a day. Breakfast, lunch, dinner, and before you go to bed. And then you start to remember them kind of for free. Let's try this example now, where we have the integral of cosecant of radical x over radical x dx. So pause the video and take a few minutes and try to come up with u and du, then restart the video when you think you've got it. Here, we can let u equal the square root of x, which is the inside of the cosecant function. Now we know square root of x is x to the 1/2. Then du is going to equal 1/2 x to the negative 1/2 dx, which means du is equal to 1/2 square root of x dx. So now I want to reorganize my integral a little so that I get my du situated. So this is equal to the integral. I can put that cosecant of radical x here, and then I have this radical x in the denominator, and I want that, and the dx. So the only thing that we are missing from our du is this 1/2, or in other words, a 2 in the denominator. So if we put a 2 in the denominator on the inside, we have to counteract with a 2 in the numerator on the outside. Remember, we have just multiplied by 1 in the form of 2 times 1/2. Now we are ready to do our substitutions. The 2 out front still remains there, that constant. Then we have integral. Then we have cosecant of radical x, which is going to get replaced with cosecant of u, because remember, u is only the radical x part, so we still need to write the cosecant. And then here, this whole entire expression is going to get replaced with du, and that's because we have this definition over here. So let's bring down the equal sign and that constant of 2, and we just learned that the integral of cosecant u du, we can use this rule right here and replace the x everywhere in the rule with u. So this is going to be negative natural log absolute value cosecant of u plus cotangent of u plus a constant. And remember, we can always just throw the plus c out on the end. Because this was an indefinite integral, we have to go back to the x variable. So this is going to equal negative 2 natural log absolute value of cosecant radical x plus cotangent radical x plus c. Sometimes we have to use polynomial long division to simplify integration. Take a look at this example where we have to do the integral of the quantity 2x cubed plus 7x over the quantity x squared plus 3 dx. Now, there's no way that the numerator could ever be the derivative of the denominator because the degree of the numerator is higher than the degree of the denominator. So what we're going to do is use polynomial long division to rework this integrand into an expression that we can integrate. So let's do this division. We have x squared plus 3 on the outside On the inside, we have 2x cubed plus, we should fill in with 0x squared plus 7x. We don't know if we'll need that x squared term or not. So for x squared to become 2x cubed, we need to multiply by 2x. Then we have 2x cubed, and we would get plus 6x. So that jumps over here. So we didn't actually need that one, but you don't know when you start out. Now we have to subtract. These two cancel out. That was the whole point. Then we have 7x minus 6x is equal to x. And then that remainder goes up on the top as x over x squared plus 3. So now we can rewrite this original integral into the integral of the quantity 2x plus x over x squared plus 3, close the parentheses, dx. Now we're going to break these two up into two separate integrals. So we get the integral of 2x dx plus the integral of x over x squared plus 3 dx. Now this is going to equal this first integral, really easy to do. We have 2 times x squared over 2. Now we know we would get a plus c from this integral and another plus c from this integral, so we're going to just tack on 1 plus c at the end. So let's bring down this plus sign. Now here we are going to need to do a u du substitution. So if we let u equal x squared plus 3, then du is going to equal 2x dx. And you can see in your integral, you almost have that. You're just missing the 2 because you already have the x dx. So if we multiply by 1 in the form of 2 times 1/2, we put a 2 in the numerator inside, so we have to put a 2 in the denominator outside. Now we're ready to do our substitution here. So this becomes 1/2 times the integral. In the denominator, we have x squared plus 3, which we are going to replace with u. And in the numerator, we have 2x dx, which can get replaced with du. And remember, we still have that plus c coming. We're just going to put it on the end. So let's continue to simplify. This first term becomes x squared. Bring down the plus sign. And this second term is going to integrate to become 1/2 natural log absolute value of u, and now we'll go ahead and put on that plus c. Because this was an indefinite integral, we have to go back to the x variable. So now we have this is equal to x squared plus 1/2 of the natural log of the absolute value of x squared plus 3 plus c. Now this is not quite in simplest form yet. Because we actually know something about the quantity x squared plus 3, in that we know that it's always going to be positive. So since x squared plus 3 is greater than 0 for all values of x, we can drop the absolute value symbols. And anytime you can drop a function, that definitely makes your result simpler. So then this is going to become x squared plus 1/2 natural log of x squared plus 3, this time in parentheses, so we don't have to do an absolute value function, plus c. Now, sometimes you will see this result written with this 1/2 brought up as an exponent, so it could look like x squared plus the natural log of the square root of x squared plus 3 plus c. And either of these forms would be just fine.